This video will demonstrate how to conduct a correlation analysis in R. We're going to start by loading up our packages. I'll assume you already have installed the example data package. If you haven't installed any of these other packages, using the pacman package will do so for you. Okay, now let's have a look at some of the functions we'll be using. All of these have to do with correlation. First, it's a built-in core function, and you can also see a function for covariance in there as well. See a core test function that is also built into R, and this is to test correlations, the significance of them. And then we have a function from HMIS package for looking at the significance of correlations as well. Now, the hypothesis that we're going to test today is the null will be there is no correlation between average combined SAT scores and minority serving institution flag. If you don't remember that those variables from our Carnegie data set, there they are. And we'll scroll down a bit here until we get to the MSI minority serving institution flag. And if we scroll back up just a little bit, actually down a little bit, there's our combined math SAT verbal scores. And then, of course, the alternative that there is a correlation between those two variables. So let's start out by grabbing just variables of interest. And I'm going to grab from associate degree through medical, and then rooms through SAT combined. So I'm grabbing these variables, and you see these missing values in there. And we can handle these missing values in a number of different ways. For this particular analysis, I'm just going to remove them. And of course, you need to justify why you're doing what you're doing with handling missing values. It probably is not the most appropriate, but for this demonstration, that's what we'll do. We'll see that that takes us down to about 1,300 rows, right? I'm also going to take that same exact output and coerce it into a matrix. And the reason I'm going to do that is because the R core function requires a matrix, and you can see what that looks like here. Slightly different. It's kind of difficult to see. I guess if we see the first 10 rows and 10 columns, it's a little easier to see. So we can see it looks similar to the tibble, but it definitely has a different structure. Okay. Now let's go ahead and visualize those two variables. And one of the best ways to visualize correlations is using jitter. One caveat here is that the indicator for minority serving schools is a binary variable. And you can do a binary variable with correlation, so long as you have two levels. I guess that would be the definition of a binary variable. But we'll see that it's not going to make a nice scatter plot in the typical sense. I use geom jitter just because the points will be laying on top of each other. This looks more like a strip plot. You can see height, I didn't jitter at all because there's no need for it. But width, I jittered about 0.1. And then I added some alpha there to deal with overplotting. So that's useful. We can see that the SATs for non-MSI schools tend to be higher if we kind of eyeball it. And for MSI schools, we see the SATs tend to be, on average, a little bit lower. Okay, now we need to compute a test or a statistic, and we're going to start by computing a correlation, right? And I'm going to first look at correlation between those two variables. That is the SAT and the MSI variables. And we'll see that it has a correlation of negative 0.26. So we can see that the MSI variable tends to have a negative relationship, which we saw in the graph with the SAT scores, right? And the covariance of that is negative 13. It's a little more difficult to understand covariance other than the direction of the effect, but it's necessary to compute correlation, right? So I think correlation is actually not too bad to understand. So I'm going to first start by selecting just those variables, right? And I'm going to go ahead and we're going to compute a couple things. And the first thing we're going to compute is the deviation of the SAT scores from the mean, right? So all that is SAT score, each individual score, minus the mean. We're going to do the same thing for MSI. We're going to just take the mean of MSI. By the way, the mean of this logical will be the proportion of schools that are MSI. So I think that's an interesting side trip we can take for a second. Grab it and take mean of that. And you can see that about 14% of schools have this minority serving flag on them. So anyhow, we can take the MSI individual. That'll be 0 or 1 because it's logical, true or false. And we can minus the mean of 0.14 from it. So now we have two deviation scores, two vectors, and we're doing that inside of a mutate. And one more thing we're going to do, we're going to take the interaction in a sense between those two. So we're going to take the deviation for SAT and the deviation for MSI, and we're going to multiply them together in a new variable. Okay, so let's go ahead and see what that looks like. So all fairly easy to compute. See those columns, right? So for instance here, we took 960 minus whatever the mean is for the SATs, and that's where we're at there. You can see that for this MSI, it was 0. We minus the mean, so we get negative 0.14. Then we multiply those two values together to get negative 1.3. And I did want to show that formula that we just did. We computed the covariance, so we took every single of the first variable every single value minus its mean, times the second variable, every single value minus its mean. We times those two together, and now we're going to we're going to sum all these up. We're going to divide by n minus 1 to give us the covariance, right? So let's go ahead and do that. And here we have that sum of all those deviances, or co-deviates, I guess we'll call it. That's not really a word. This column here where we multiply the deviation of the SATs times the deviation of MSI, and we sum that all together, right? And we divide that by n minus 1, and that gives us our covariance. And let's go ahead and see how that compares up above. So I realized we had an error because I had computed a covariance that was rather large, and the built-in R function said, hey, this is not correct. And my error was I had done this on a test set with empty cars, and I left that in there instead of DAT. So let's go ahead and recompute some things. First of all, let's see what the built-in R says. For covariance, negative 13.33. And let's go ahead and rerun DAT again. And now let's compute that covariance with the formula we just saw in the PowerPoint. And we can see that indeed that value matches what we computed with the built-in R function. Okay, now we're going to want to compute the correlation. That's R xy here, and so we're going to take that covariance that we just computed divided by the standard deviation of x times the standard deviation of y. And we have all the information we need to compute standard deviation for those two variables pretty readily. So we have their deviation from the mean here and here in this column. So all you need to do then is to square each of those values up, take the sum of those, divide it by the number of rows minus 1, so n minus 1, and take the square root of that. So we just there computed the standard deviation for those two scores, and you can see them. We could do that by hand as well, or not by hand. We could do that with the built-in R function as well. I'm just showing you how to do it by hand in case you're interested. You can see that's indeed what we get. Compute the same with the built-in SD function, and again, that's what we get for the standard deviation. So now computing R is a rather simple act. We just take the covariance divided by those two standard deviations multiplied together, and we get the correlation there. And let's see if that matches the correlation that we used R to compute. And it does not match because that is the covariance. There's the correlation. So it's a negative, I'd say small to moderate correlation, negative correlation, right? And let's go ahead and compute the degrees of freedom on that, and that's just n minus 2, because of your degrees of freedom, and you're estimating two different values because you have two different variables. And the t statistic for that is pretty simple to compute. That's just r times the square root of the degrees of freedom divided by 1 minus r squared. And you can compute z values for these. It's a little more difficult and not as often used, so the t scores typically are the way to go. And then you simply can look that up in your t chart. And here's our t chart. We want two tails for for 95% confidence. So we come down here. We can see with 1,000 values, that's over 1,000 values for our degrees of freedom. It approximates the normality. So we need a score bigger than 1.96 for a t-score, which we are well beyond that. So this is definitely a significant difference between these two groups. Let's go ahead again and see the core test with the built-in functionality. But then we could also do the test of significance with the built-in core test here. And note that I had to wrap it with as integer. And all that does is take the values that are logical and turn them to integer. So we run that test of significance. You can see that indeed we get the same t value that we computed by hand, or within reason. The degrees of freedom are n minus 2. So that core test is a nice built-in function. I do want to show you what happens if you don't wrap it with as integer. You get a nasty error. So one way we could have dealt with that is we could have handled that up above when we first created the data. Cool little function in dplyr is mutate if. And you can give it a condition. So if is logical, go ahead and make it as integer. And let's go ahead and run that and see what it looks like. And we can see that those integer values like MSI have been turned to, or I'm sorry, those logical values have been turned to integer. So we can handle that with our cleaning instead if we want to. And now let's go ahead and run that core test. And it works perfectly fine without coercing it to an integer. So how would we write that up? We'd say something along the lines of combined SAT scores display a weak to moderate negative correlation with schools with a minority flag. And we say the R, because that's our test statistic. You can also use the subscript xy on that as well. Then the degrees of freedom, that's n minus 2. So that's 1327 equals, and what was our R? Our R was negative 0.26. P is less than 0.05 was our preset alpha level. Now I must admit that I have not computed a correlation between two variables since my initial intro to stats classes. Typically, I compute a table of correlations all at once, right? So there's some built-in functions in R to do this, and if we wanted to visualize them, we could use the SPLOM. So that would give us multiple. It'll give us multiple of the scatter plots together as a matrix. I was a bit remiss up above. I forgot to mention this. With your R value. So RStudio froze up on me because that SPLOM was overwhelming to plot to the plot console window. So I went ahead and saved that as a PDF, and we'll view it as a PDF. I do want to get back to something that I missed up above here I want to talk about, and that is interpretation of correlations, Pearson correlations, the R, that is. And you can take the R, and we see that R there, and you can go ahead and if you square that value, this gives you the proportion of explained variance in Y from X. So we can say that 7% of the variability in SAT scores in the dataset is accounted for by schools with MSI flags on them. Also note that correlations themselves, as Andy Field points out, can be interpreted as effect sizes. So depending on the field you're in, smaller correlations, maybe between 0 and 3, moderate maybe 3 to 7, and large maybe above 7. Those cut points can change depending on the field you're in, but they can be interpreted as effect sizes as well. So let's get back to the scatter plot matrix, and I have it dumped out here. It's kind of overwhelming, but each and every single one of these, it's like a correlation table, but every single one of these squares is a little scatter plot, and you can see the plot between the variables. So you can see some here, for instance. Let's go ahead and grab a way to highlight it. You can see some have a tighter correlation. It's kind of hard to tell what those variables are. It looks like master's degree and something else. It's kind of hard to tell. Something here, I'm not really sure. It's kind of difficult just because of the size of this thing. So probably scatter plot matrices are better off for a fewer number of variables. You can see some variables that have looks to me to be like binary type variables. We already know that, like the MSI variable is binary, so you see basically two columns. You see some with a bit more variability here, for instance, over others. So this table is definitely interpretable, but this one here tends to be a bit overwhelming. So let's get back to the code itself. So the same function we used for a correlation with a single variable, we can use for a whole table. So we take the Carnegie with no NAs in it. It's a bit large, but you can see that. We can just run the core on that. You can see that itself is still pretty large. If we wanted to, we could wrap it with, actually we'll pipe onto the next line. Round, we'll say 1 digit, maybe you want 2 digits. Let's give ourselves a little more real estate here. So there it is with 1 digit. Still kind of hard to see what's what, so you can see some negative values popping out. You see the diagonals are all 1, which makes sense. But it's kind of hard to make. I see a couple stronger correlations here between fall enrollment 13 and doc degrees. I see fall enrollment and bachelor degrees, a strong correlation near 1. What if you wanted to do a test of significance for all these? This is where the R core function works, and we're going to get an error here by doing this. We just passed it the same data set, and it can't handle that. So we need to give it the matrix version. So just wrap it with as matrix. Now we're looking at something a bit more useful. In the lower table here, or matrix, are the p-values. So you can see things that are probably significant. Keep in mind about family-wise error rates. And then up above you have the correlation table as well. Still pretty overwhelming and difficult to figure out what's what in this whole needle in a haystack. Right? Let me get a little more real estate and run that again. So it can be useful for dumping these out for the purposes of publications or such. But if you really want to understand what's going on, the core plot function from the core plot package really does a very nice job of visualizing correlations. So let's go ahead and view that correlation. And it does it with not much real estate either. So I'm going to make it a little bigger, just to make it a little bigger. But you can see dark blue are very positive towards 1. Darker red is a -1. So we're looking for bigger circles. Those means bigger correlations. Small circles mean smaller correlations. We can see, looking around here, the negative correlations that we kind of discovered before between SAT scores and MSI, and then also historically black colleges and universities, similar type of variable, have a negative correlation with SAT scores. You can see very positive correlations. For instance, fall enrollment with bachelor's degrees, that's not really unexpected. Full enrollment, 14 with rooms. I really don't understand what that strength of association is, and it could just be spurious correlation as well. So this video demonstrated how to perform correlation analysis, how to do it between two variables, look at tests of significance, how you could write that up, and then also looked at how you could do an entire table of correlations with numeric data, and then how you could find significance on that, and how you could also visualize it as well. So a very useful technique for finding associations between numeric variables.